Mrs. Valero, floor is yours.
Thank you very much. Do you see my presentation?
Yes.
Okay, perfect. Well, thanks a lot for the GF for inviting me. And thanks a lot also for the translator to translate my words. I hope I will not be too fast. And I would like to talk about the limits of circular economy and also show which are some of our outcomes that we have been doing, we have been researching during the last 15 years now. And well, the outline of my presentation, a very quick presentation looks like this. We will ask ourselves about whether it is feasible, the green energy transition as it is now, then also question ourselves about towards the circular economy, and then some final reflections. Well, first of all, and very quickly, because I think Eva did this introduction very well about the challenges of the green energy transition. And we know that new materials for these decarbonized economies require many different raw materials, which are in fact scarce. And obviously this includes the electrical vehicle and the batteries, which is the topic of today's conference. So I am asking, or we are asking ourselves, is this a green economy or a multicolor economy? Because wind energy needs neodymium, dysprosium, praseodymium, samarium, cobalt, or batteries that I am putting here in bold. And as Thomas said, need nickel, manganese, cobalt, cadmium, etc. So this is truly a multicolor economy. We will be dependent on many different raw materials. And well, such as the energy, the fossil fuel energy is becoming depleted, for instance, oil or gas, not so much coal, but mines, raw material mines get also exhausted. And we have been doing in my institute different studies regarding which is the peak, the probable peak of many different elements from the periodic table. And you can see here a graph, but I can tell you that the result was because of this exponential increase in the demand of raw materials, the peak of production of most essential minerals could be reached before the end of the 21st century. And a good number of them even before the middle of this century. But this is not the only problem. The other problem is the energy fact. So energy, if we look at the mining energy as a function of the grade of the mines, that means of the concentration of the metals in the mines, we see, and this is a consequence of the second law of thermodynamics, that as the mine gets depleted, then the energy required to extract the next ton of material increases exponentially. And we have done a study for thousands of mines around the world, and the trend is the same. So we will probably face not only depleting ore grades, but also increasing energy consumption, increasing water consumption, increasing environmental impacts. And this is a problem because currently mining is done with fossil fuels. So there is here the problem of we do not want to rely on fossil fuels, and yet we are shifting the dependency of fossil fuels into minerals, which also require energy. And today that is in terms of fossil energy. And let me show you, because today's topic is about batteries, and lithium is obviously the main element in lithium-ion batteries. And what about, which is the future availability projection? So we have done this exercise, the peak of lithium, considering different scenarios regarding how much is there on the ground, because many say, well, there's enough lithium in that lithium triangle, as Thomas said, or also in Australia through spodumene. However, because of this exponential increase, even the best or the optimistic values regarding reserves shift the peak just a couple of years. So it's maybe the minimum would be 2032. Then we can shift if more reserves are found to 2037, 2049, considering resources and not reserves. That means quantity of available resources, which we know they are there somehow, but it is nowadays difficult to extract in an economical way. The peak shifts to 2060 and considering water 2078. So we have really scarcity about resources. And as you know, lithium is not the most scarce. Cobalt is scarcer, for instance, than that. So we have done also an analysis of supply and demand for minerals regarding the energy transition. And we found that demand between today and 2050 could be greater than reserves for those minerals appearing here. Cobalt, which is essential for batteries, lithium, nickel, also platinum will be at risk. Here you can see, depending on the technologies, which are the most, the elements that have a very high or high risk of limited supply. And cobalt is there, lithium is there, manganese is there, or nickel is there. And we know, and Eva and Thomas already said, we know we rely on other countries, for instance, China, the most important one. And well, China has the resources. If China doesn't have the resources, it just buys. China is already buying mines and enormous surfaces in Africa or in South Africa. So if they do not have the mines, they get them, or they get the raw materials and they refine them that then we use in Europe. So we completely rely on China and some other countries. What do we have in Europe? Do we have the technology? Well, yes, we have technology, but the Chinese also have the technology. What do we have? We have waste. So waste is a problem, or waste is an opportunity. And I believe waste can be an opportunity. Therefore, we should take advantage of all the technological artifacts that surround us in order to produce those valuable raw materials. So the new alarm signs, the critical raw materials for the European Union, you have here the list, 30 elements. And this list is increasing year after year. And in the end, we will have that the whole periodic table is critical. So if there are some raw materials that are more critical than others, why are we currently assessing, designing, and doing policy making, considering that 1 kilogram of iron has the same value of 1 kilogram of cobalt? Minerals are not equally scarce. However, products and regulations are being designed as if they were so. And we said this cannot be the way to go. We have to change this point of view. So what if manufacturers, users, recyclers, and policymakers knew from the outset how critical are their products? Then probably they would be used in a better way, and a better circular economy could be achieved. So this is what we did. We assessed raw materials in terms of the scarcity that they have in the crust and the energy required to mine, beneficiate, and refine them. And you have here in different colors the quality of raw materials. And you can see that those related to batteries are in red. So the scarcer and the more difficult to beneficiate and refine an element, the greater what we have called rarity, the thermodynamic rarity, which is a physical criticality. So we have done several studies with this indicator, assessing which is the rarity or the criticality, the physical criticality of different artifacts, of different technologies. And in fact, all IT technologies are very, very critical from a thermodynamic point of view. And it tops the electric vehicle. The electric vehicle is an authentic road mine, and we have to do something with the wastes of that vehicle, because otherwise we will have to rely more and more on mines that are being exhausted. If we analyze the different technologies with this indicator, and we did so together with a German institute, what we got is that, in fact, the most, let's say, efficient technologies from an energy point of view are less efficient from a raw material point of view. So, for instance, an LED light bulb is more efficient than an incandescent light bulb, yet it has so many tiny elements inside that it makes them impossible to recover, and therefore I ask myself whether an LED is more sustainable than a conventional incandescent lamp. So, and now going back to the car sector, and we are closely working with SEAT, with the Volkswagen Group, for different studies regarding the criticality of the vehicles and how to design them more efficiently, where we have assessed in terms of mass, which is the composition of a conventional vehicle, combustion engine vehicle, but also different types of electric vehicles. And these types of vehicles were already mentioned by Tomasz, and these depend on the quantity of cobalt mainly. So as you see, first of all, in mass terms, electric vehicles will be heavier. They will contain more metals. But, well, this is not really an indicator that assess you what is the criticality of your automobiles, because we have done this in terms of rarity, and the situation is completely different, because an electric vehicle from a raw materials point of view is much less sustainable, about 3 times less sustainable than a conventional vehicle. Why? Because it contains scarce metals, and one of the most important ones is cobalt. Now, the automobile industry knows already the problems of supply, and therefore they are doing whatever it is in their hands to reduce that cobalt contents. And that's why they are also developing new electric vehicles, even if they haven't even appeared to the market, but they are already thinking in reducing that amount of critical raw materials. And with electrification, this will become worse, because all electric and electronic materials contain such rare elements that are very scarce. And we have done also an analysis regarding the strategic raw materials for the automotive industry. And in red, you can see here those that are specifically strategic. And here you see, for instance, nickel. Nickel is currently not included in that criticality list, but I am sure in the next list, nickel will be one of the most important candidates to be introduced, because it is extremely important for batteries. So, alarm signal, raw material supply risk, we have to move towards a circular economy. And we have assessed which should be the recycling rates, the annual growth of recycling rates, in order not to reach those supply risks that I mentioned before, in order that the reserves can somehow compensate with this increasing demand. The numbers, well, might sound important, and they are very important, because the recycling share by 2050, some of them might increase by half. And there's 2 problems. First of all, the fact that we do not have technologies at the end of their life, so the stock is not there. This was mentioned by Eva, but also what I will comment now is the fact that currently recycling rates are extremely low. So most of these elements which really are scarce have recycling rates below 1%. And why is that? Well, why? Let me ask ourselves towards the circular economy. Well, Eva mentioned before, what is the circular economy? It's about sharing, repairing, reusing, remanufacturing, recycling, and most important, as she mentioned, is not using, reducing, okay? But okay, let's think that we have a technology, whatever, a mobile phone, for instance, or a car, an electric vehicle. What do we have there? Well, what we have is that the tendency is increasingly complex products and materials, and such scarce elements which are included in these generations of different mobile phones are in milligrams or micrograms or nanograms, which are completely impossible to recycle. It's impossible to recycle them, such as the LED lamp that I already mentioned before. So we have chemodiversity in common products. We have mixtures of chemical elements that do not appear in nature. And there are no recycling processes or metallurgical processes developed enough in order to separate, first of all, this artificial mixture of products that do not appear in nature, and also in such small quantities. So let's go back to the case of the car. We have assessed, as I mentioned, what is the criticality of a car, and the legislation regarding cars is that you should recycle, or recyclers should recover 90% of the car in terms of weight, in terms of mass. Okay, but what is that? Well, actually, the recycling processes of end-of-life cars are very simple processes and cost-effective based on physical procedures. It's about dismantling of batteries and fluids, then we shred them. Through magnetic separation or density separation, we remove, or we separate the steel from the non-ferrous and from plastics, and then we go smelting. And what do we smelt? Well, we smelt all the steel together, and the result is the worst quality steel that we could ever have. So in fact, 95% recycling is not a reality, or it is only a partial reality, because where's the gold, where's the cobalt, where's the neodymium, where's the platinum? All such elements which are in very small quantities just become lost or become downcycled in low quality steel, for instance. So in the end, we need more fresh raw materials to be introduced in order to produce a new car. So with 90% recycling of the car, we cannot make 95% of a new car, because there are thermodynamic limits. Metal mixology applies here in recycling, because there are always irreversible losses at the end of life. So if you want to recover steel or iron, you go through this, let's say, part of the metal wheel, which was developed by my colleague Markus Reuter and his collaborators. And you will lose all the copper, all the rare earths, and other elements that form part of that mixture, right? So I'm sorry, but there is no circular economy, because every time we want to recycle, there is some part that becomes lost. And in every circle, that quantity lost becomes greater and greater. So I think it is better to speak about the spiral economy and not the circular economy. The economy will never be circular, and we need to know that this is a fact, this is a physical fact, and then design products accordingly. And for the same example of the car, we did a recyclability assessment, and we designed with a special software the most complex recycling facility that we could ever have, so that to obtain all the elements that could be obtained out of the key parts, okay? So even doing so, and this plan doesn't exist in reality, we could get, well, almost 90% of precious metals, base metals, and some others. Then by 50%, also some scarce metals like germanium, indium, or tin, but then we lose completely to the slags, lithium, tantalum, or rare earths, or molybdenum, etc. So even with the most sophisticated recycling plan, there are many, many losses. And why is this so? Well, because the car is not thought to be recycled. And the challenge of batteries recycling. Tomasz already said what is a lithium-ion battery. And we ask ourselves, can we learn from traditional batteries recycling? Well, in part, yes, because almost all lead-acid batteries are currently recycled, at least in Europe. And this is so because of good and effective collection channels, and also because the chemistry is here facilitated because, and here this is the lead acid battery example, because lead acid batteries are composed by 70% of lead, and lead is a heavy metal and can be easily recycled, can be easily separated from the rest of the materials. Yet, a typical lithium-ion cells consists of 4 main components, including the cathode, the anode, the negative electrode, a separator, and an electrolyte. And most of the critical materials are in the cathode, yet they are only one small part of the whole composition of the battery. And this battery is an example of an NMC 622, but you see here it's 31.8%, whereas here the lead is almost 70%. And then we have other different materials that need to be separated in order to come into these cathodic materials. So, can we learn from traditional batteries? Yes, but unfortunately the chemistry is very different and it needs to be still developed. So what is the challenge of lithium-ion batteries recycling? The battery needs first to be discharged. Then it needs to be dismantled, where the electrodes and the electrolyte are separated. Then the electrode is recovered, all right? And the rest become crushed and screened to separate the plastics, the graphite, and the metallic components. So once we have this crushed material, which is a mixture, an entropic mixture of many elements, then it follows pyrometallurgy, a pyrometallurgical process, usually, and this involves high temperature smelting to recover nickel, cobalt, or copper. However, all the lithium is lost in the slags. So if you want to go further, then you should obtain, or you should go with the hydrometallurgical steps, and this route would be carried out through leaching by inorganic acids to facilitate metal recovery from dissolved metal solutions. And this obviously requires the introduction of expensive and toxic materials. And after that, it follows the final step, which would be separation and purification through different techniques, such as solvent extraction, chemical precipitation or electrochemical deposition. And well, we have different challenges. First of all, there are only a few companies in Europe that can recover some and not all of the cathodic elements. We need an infrastructure to recover all such elements. Then there are thermodynamic limits and metal mixology, because as I said, if you go through the one metallurgical route, then you will lose all the lithium, for instance. And then you have also toxic binders there of the cathode, which are difficult to remove just because it is not designed for recycling. And another important barrier of this is that because of technological advances, because we want to reduce the consumption, for instance, of cobalt, which is very critical, then we have different configurations of cathodic materials. So we have LCO, NMC, LFP, NCA, LMO, etc., that were explained by Thomas. So recyclers get a mixture of materials and they do not really know what they have in that mixture after the crushing processes. So this becomes even more difficult for the recycling process. So recovery of valuable metals from lithium-ion batteries is still in its infancy. There is a lacking of metallurgical infrastructure in Europe. There are technological barriers that I mentioned, inefficient collection, safety concern, and also lack of regulations and policies for spent batteries. And the most important is that there is no communication between producers and recycling. So there is a lack of design for recycling, not only in batteries, but in all the products. And some final reflections, and I finish here. So the management of critical raw materials should be based on concepts such as rarity, what I explained, and recoverability. So we need to consider the criticality of products and also the recoverability of products, because in that way we will have a sense of conservation, because what we have is rare. It cannot be the case that we switch our telephones or whatever every 6 months. This is completely unsustainable. So when developing new materials and products, manufacturers need to think in the criticality of materials and reduce, for instance, cobalt, etc. So avoid what is scarce, but also the recoverability of the first, second, third, etc. materials, and avoid the use of materials and mixtures that cannot be recovered at the end of life. So they do not, or we do not have to omit thermodynamic limits that exist. So we need awareness rising by smart and smart EOL. We need a robust information infrastructure of materials and products across the whole value chain, from the mine to the consumer, so that wastes can become again raw materials. And something also very important, a full and flexible metallurgical infrastructure able to recover minor but valuable metals. Wastes in Europe are an opportunity, but if we do not invest on this infrastructure, then we still need to rely on third countries. So it is the hour for humanity to begin to adequately manage its non-renewable resources with intelligence and order. So I propose to move towards an in-spiral economy. If you want to know more about these topics, there's a book that will be released very soon. And thanks for your attention.